Hello everyone. So I want to talk about Gauss's law today, and I'm going to try to do this quickly and in one take because the world seems to be very bandwidth limited and YouTube is incredibly slow today. I also want you to understand the conceptual foundations of Gauss's law, so here is another physics basement episode that will hopefully help you understand Gauss's law a bit better. Okay, there's a few sections to this, chapter 22 in Giancoli. The first one is electric flux. We're going to cover that. We're going to cover Gauss's law and then some of its applications. You can read that experimental basis of Gauss's law section. That's interesting. Okay, electric flux. So, electric flux has this symbol phi e here, and the electric flux through some surface A is just the amount of electric field lines that are passing through that surface perpendicular to the face of the surface. So it's exactly the same type of concept as, say, hydraulic flux, the amount of water passing through some surface. And keep in mind that the surface there doesn't have to be a real physical surface. It can be a mathematical surface, right? It's any kind of surface that you want to define. I'll talk about that more. But it's equal to, right, the magnitude of the electric flux times the surface area A times the cosine of the angle between those two, or another way of thinking about it is just the dot product between the electric flux and the area vector A, where the area vector A is this vector that has a magnitude that's equal to the surface area of that area in question, and has a direction just pointing normal to the surface, itself. Okay. Now, you probably remember what scalar products are, but just very briefly, I wanted to include some of the stuff from chapter 7 of the textbook where this was introduced, in case you forgot when we talked about work in physics 1. So remember, work is the dot product between force and distance, right? Work is what happens when a force is applied over a distance, and it was equal to force times distance times the cosine of the angle between the force and the distance, right? So this is called the dot product or the scalar product. You probably remember this from physics 1. I hope you do. If not, go back and review it. So you remember that you can take the magnitude of the two vectors times the cosine of the angle between the two, or another way of defining it, mathematically equivalent, actually, is to take the individual components, the x components, multiply them together, the y components, multiply them together, and add those two products. Okay. Now, the electric flux. Let's do an example problem. So here, we're going to calculate the electric flux going through the rectangle that's shown here, where the rectangle is 10 centimeters by 20 centimeters. The electric field is uniform at 200 newtons per coulomb, and I'm just going to say that it's pointing in the x direction. We'll call this, right, the x-axis, and that the y-axis. And the electric field so the area is angled at a 30-degree angle to the electric field E. Okay, so I've already gone through the calculation here, but so it's 10 by 20, so that means the area is 0.02 meters squared, multiplying those two together, right? The area vector, the area unit vector is given here. It's, right, the cosine of this angle is AX, and AY is here the sine of this angle times the overall area A, right? So the unit vector here is pointing along this direction, out normal to the surface. So that means, so if I take the product of this overall area here and the unit vector along the area vector here, then I have my total area vector A. And remember, E is constant, and it's right along the x-axis. So I can take the dot product between these two, and that will just give me 200 newtons per coulomb, the electric field, times the magnitude of the area vector times the cosine of the angle between the two, which is 3.5 Newton meters squared per coulomb. So that's as fancy as this is as very cumbersome units. There's no shorter version of this. These are the units for the electric field. So these are the SI units for electric flux, sorry. All right, so there's an example problem for you. Okay, now, important question. What if E is not constant over that entire area? Well, going back to this same question from Chapter 7, when we talked about work in Physics 1, remember that the work done by a varying force is, you can't just take this simple dot product F dot D, right, if the force is varying with distance. But what you can do is break that distance traveled up into little parts and take the dot product between each one of these little tiny elements. Right here it's broken up into 7 different pieces. Well, for a force that varies, right, you can approximate this by dividing this distance up into small pieces. You can even divide it up into an infinite number of infinitesimally small pieces, right? And in that limit, you have that the work is the area under this force distance curve, right? It's the integral. So what you ended up with in Chapter 7 was this integral from a starting point to an ending point of force dot with these little distance elements dl, right? Which is the exact same thing as saying f cosine theta dl, where this cosine theta has to reflect the angle for each part of each distance element that you're integrating along. Okay, same thing in the case of electric flux when the flux is varying through a surface. So here it's specifically talking about a closed surface, but in general, you can use that the electric flux through any surface is just the integral of E dot dA. Okay, so you're going to take, so this is exactly the same thing as saying E dot A in the case that E does not vary over A, but in the limit where, or in the case where E changes over different elements of dA, then what you're going to have to do is take this area, divide it up into tiny little pieces, and take the dot product between the electric field here in this single part here with the area element dA that makes up this tiny square. And then the electric field, it can be allowed to change over the course, over this surface into different values. And when you sum these things together, then you end up with the proper answer, right? That reflects this change in the electric field over different parts of the surface. Okay, so this is true in general. Now here this slide is talking about the flux through a closed surface. So a closed surface is just saying that it's an area that has no boundaries to it. It is all wrapped around on top of itself. Okay, what do I mean by that? I mean that it's the boundary of a 3D volume, right? With no edges to it. So here's so think about it. How many edges are there on the surface area surrounding a sphere? Right? There are none. Okay? Here I drew a square. Square has 4 edges. There are none on the area that makes up the surface area of a sphere, right? The whole thing is entirely connected. So this is a closed surface. Okay, when we talk about this integral over a closed surface, that's when this little circle shows up around the integral. This thing tells you to do the integral over a closed surface. Okay, this is important because Gauss's law is going to have one of these integrals in there, and Gauss's law will not hold unless you do this integral over a closed surface. It's very important. A closed surface is the boundary of some 3D surface, any 3D surface. Okay. So the flux through a closed surface then is made up of one of these integrals that goes around the boundary of some volume. So you can see here the electric field line, one electric field line is shown passing through here, right? The dot product between E and some dA, some area element pointing out normal to the surface area, shows up. So you see it here, and you see another one. This electric field line goes right through the whole surface, right? And it's pointing out in this direction here. So each one of these small patches would contribute to the overall flux going out through this whole surface here. Okay, on to Gauss's law. Gauss's law states that the net number of electric field lines through a surface is proportional to the charge enclosed within that surface. Okay, so Gauss's law states here is the electric flux through a closed surface on the left-hand side here. Here is the amount of charge inside of that surface divided by epsilon naught on the right-hand side. So that means the electric flux passing through a closed surface is determined entirely by the amount of charge enclosed within the surface. It does not depend on anything else. If there is no charge inside of some surface, then the net electric flux passing through that surface is zero. This is true only for closed surfaces. Keep that in mind. And the reason why we use Gauss's law at all in physics 2 is because this can be used to find the electric field in situations with a high degree of symmetry. Okay, if there's not a high degree of symmetry in the problem, then Gauss's law is still true, but it's probably not going to be helpful for you. Okay, let's just try and drive this home a little bit more. I'm going to make the claim that this actually makes sense. Okay, so here I have a few different Gaussian surfaces drawn in green. Okay, the green is Gaussian surfaces. In red, I have some charges, and in blue, I'm going to draw some electric field lines. Okay, so remember that the Gaussian surfaces, I've just drawn 3 cubes here. Just remember that Gaussian surfaces, these are mathematical surfaces. They don't need to be physical surfaces. They can be, right, I can talk about a sphere that's like a real sphere, a basketball that I hold on to, or I can talk about a mathematical sphere. I can say the set of all points surrounding my fingertip. The set of all points 10 centimeters away from the tip of my finger is a mathematical sphere, right? It doesn't exist physically. There's nothing there. There's no shape there. However, that is a well-defined mathematical surface. The set of points 10 centimeters away from my fingertip. That is a perfectly fine mathematical surface. Okay. Remember so Walter Lewin used this analogy of electric field lines, or of charges being like sources or sinks for electric field lines. So you can think about positive charges as being like blowing sources of like a fan or something that's blowing air out, and negative negative charges as like things that are sucking air in, right? So if I have a positive charge, remember, here, and I have a negative charge here, then the electric field lines are going to point out from positive charges, and they're going to point towards negative charges, right? They point in. So you can think about it as like, if you sit near this plus thing here, and we're just going to make an analogy between electric field lines and air blowing, okay? This is a source of electric field lines, this positive charge. I can think about it as like some kind of blowing, a leaf blower or something blowing air out, right? And I can think of this negative charge as being, electric field lines point in towards it, or I could also think about it as it being the opposite. It's a vacuum, right? It's sucking air in. So if I wanted to draw the way that the air will flow, right, it's going to go from the positive charges to the negative charges, right? And so this will go out and wrap around, and it'll come back over here. This will go out, around, and it'll come back there, right? The electric field lines point out from these positive charges. They point in towards these negative charges. Okay, what does this have to do with Gauss's law? Okay, let's think about it. So let's say that I want to find the electric flux here through some surface, through this surface right over here, right, where there's just a negative charge inside of it. Well, the electric field lines would have to be pointing right in towards this negative charge here. So the flux is coming in through the surface, right, on all of these sides here. And what you would get is this net negative flux, right? Here's the electric flux, right? Each one of these, so the electric field lines would be pointing in towards the charge here. The area elements always point out normal to a surface, right? So over here on this side, the area element would be pointing out this way, right? Here on the front side, it would be pointing out towards you. dA would be pointing out towards you. Up here, dA would be pointing up, right? So dA is pointing in the opposite direction of the electric fields. So that dot product is going to be a negative quantity. You get this negative flux that surrounds a negative charge inside of a box. Okay, now should be fairly easy to convince yourself that you can do the exact opposite with a positive charge, right? A positive charge is like air blowing out, right? There's going to be electric field lines coming out from this thing in every which direction, and you're going to get this net positive flux because the area elements dA are going to point along those electric field lines in this case. Okay, cool. Now, what if, now the thing about Gauss's law that makes it worth talking about and worth dwelling on, even though it's got this weird integral with a little circle around it and stuff, the thing that makes it worth talking about is that Gauss's law is always true. Okay, it's more general than Coulomb's law. It's one of the 4 fundamental equations of electromagnetism. So there are four equations that govern the world of electromagnetism. Okay, they're called Maxwell's equations. And the first of them is Gauss's law. That's the first one that we'll be covering. Maxwell's equations are kind of the epitome of physics 2. This is what we're working our way up towards. We're working our way up towards Maxwell's equations. Once my goal is, by the end of this class, you will understand these 4 equations. You'll understand Maxwell's equations. And from those 4 equations, you can derive all electromagnetic phenomena short of anything on the quantum scale. Okay? All electromagnetic phenomena can be derived from Maxwell's 4 equations. And they also translate nicely into, with some very brief, just a few lines of derivation, you can get electromagnetic wave equations out of Maxwell's equations, which is kind of the great discovery of Maxwell. Anyway, okay, so that's all to say that Gauss's law is always, always, always true, and it's very general and it's always helpful. What that means is that the electric flux through a surface is always equal to Q enclosed over epsilon naught. So this is not just the electric flux due to Q enclosed. It's just the electric flux. So if there's charge that's sitting outside of a surface, right? Let's just say that there's a positive charge here, and there's a negative charge here. Okay, both of those will serve as sources for electric field lines, right? They'll point this way, and they'll point out, right, this way. So these things are going to contribute to the electric flux through the surface, right? They will. It's true, right? There's going to be a positive contribution from this part right here. There's going to be, well, no, there's going to be a negative contribution from this point here, right? When it goes through this side, this top part here. But when it comes out through this side here, it's going to have a corresponding positive contribution. So there'll be a negative contribution here from this when I integrate over this little part here. There's going to be a positive contribution when I integrate over this part here. What Gauss's law tells us is that the net electric flux that comes out from due to these charges that are not enclosed within the box is 0. Okay, these tiny little elements here, yes, these will have non-zero electric flux contributions, but when I sum over the entire surface area, and it has to be a closed surface, remember that, then the net effect of charges that are outside of the surface is going to be 0. And the only thing that will matter, remember our analogy of air blowing through a surface. The net amount of air blowing through a surface is only going to depend on whether you have, a leaf blower sitting inside of it, or if you have a vacuum sitting inside of it. If you have neither a leaf blower nor a vacuum inside of the surface, right, if they're just outside of the surface, then you're going to have some positive contribution over here, you're going to have some negative contribution on the other side, and overall they will cancel each other out. So that's all to say that Gauss's law is always true, and it makes sense, right, that there would have to be sources of electric fields diverging out from a location inside of the surface in order for you to have a net flux through the boundary of that surface. All right, so let's talk about Gauss's law for a point charge. So remember here, here we have a point charge Q. If we wanted to find the electric field, or if we wanted to derive the electric field that exists a distance r, a radial distance r away from a point charge Q, what you could do is, let's just say you didn't know this, you hadn't already learned this. You could use Gauss's law. What you would want to do is say, well, I'm talking about a point a distance r away from a charge Q, so I'll go out a distance r, and I will have to define for myself a Gaussian surface, okay? This Gaussian surface is not physical. It doesn't have to be physical, right? It's a mathematical surface. And what you could do is say, I'm going to take the integral around the boundary of this surface, E dot dA, right? And I'm going to use symmetry really nicely, okay? Why would we choose to use a spherical Gaussian surface to find the electric field from a point charge? Because it's symmetrical, and that makes our life easy. Okay, so if I take this integral here, the electric field diverges out from a point, right? And so if I have a surface that's spherically symmetric about that point, then E and dA are perfectly aligned everywhere along that surface, right? This is the nice thing about doing Gauss's law in spherical symmetry. You can go from this step here to this step here, right? Where this dot product just became multiplication. This you can always do in the case of spherical. In the case of spherical symmetry, right? Because dA and E are always can always be chosen such that they're along one another. Okay, now on the next line from here to here, why can you take E outside of the integral? Because the electric field is going to be the same everywhere along this surface, right? It's not going to matter which surface area element dA you're integrating over. E is going to be exactly the same because you're always the same distance away from this point here. Okay, so that's where that step comes from. Now, what is from this step to this step? Why does that happen? Because the area of a sphere is 4 pi r squared. Okay, I've now, my integral over the boundary of this volume, over the area that bounds this spherical volume here, is just the surface area of the sphere. Okay. So, therefore, from Gauss's law, let's stick this then into the electric flux from Gauss's law, right? We then know that E, the magnitude of the electric flux, times 4 pi r squared, the surface area, is equal to Q over epsilon naught from Gauss's law. So divide both sides of this equation by 4 pi r squared, and you have just derived the electric field distance r from a point charge Q. Great. Now, we used a sphere because it was convenient. But what's interesting about Gauss's law is that it's always true. So you could pick any shape you want. It could be any arbitrarily shaped surface like this strange amorphous blob, A2, and you would see that the same amount of flux passes through it as passes through the spherical surface, A1, right? This is true because Q enclosed is exactly the same no matter which area you choose to go around here, okay? So these two, it wouldn't matter whether you chose A1 as your Gaussian surface or A2 as your Gaussian surface, you would still get that the electric flux through that surface is just Q, which is inside of there, divided by epsilon naught. Okay, now note that if there's several point charges in there, okay, we already derived the Q enclosed over epsilon naught for one point charge enclosed within a surface. Now note that if there's several point charges in there, there's this thing that we talked about a lot called the superposition principle, right? Which just says that you would add up the contributions from the electric fields due to each individual point charge, right? You could just sum up the different electric fields in here, sum up the charges that are sourcing these fields over here, and you would get the exact same thing. So what that means is Gauss's law then can be shown to be valid for any charge distribution, right? Because any charge distribution can be thought up as a series of different point charges, right? You can always take a whole bunch of different points together, right, to define some surface or some sphere or something, right? Here I'm just drawing a circle out of a bunch of different dots, right? You can take this superposition over all of these different charges to come up with this disk of charge. That would be perfectly fine. Okay, now remember, note that this refers to the field due to charges within the Gaussian surface. So the ones outside the surface will also create fields, but their net contribution to the electric flux is going to be 0. All right, so here's a great conceptual example. Okay, so say that you are considering two different mathematical surfaces, A1 and A2, and the only charge present is the charge Q at the center of surface A1. So this one here. What is the net flux through each surface A1 and A2, which exists side by side, but remember only A1 has the charge Q inside of it. Okay, I want you to pause the video and think about this yourself, write it down, and then hit play, and I'll explain it. Okay, I'm going to take it that you've done that. All right, what's the net electric flux through surface A1? Well, it's going to be Q over epsilon naught, right? Q enclosed over epsilon naught. Okay, for A1, Q enclosed is Q. Okay, so the net flux through A1 is Q over epsilon naught. Great. Okay, what about for A2? Well, phi A2 is E right around A2, and that's going to be equal to Q enclosed over epsilon naught. What is Q enclosed for A2? What's Q enclosed for A2? It's nothing, right? It is 0. So the electric flux through A2 is equal to 0 because there's no charge inside of it.